We're looking at the knowledge area, electricity and magnetism, and we're dealing with the concept of resistance. So resistance is defined as a property of a material which causes it to oppose the flow of charges. Right? So if the resistance is high, it opposes the flow of electrons to a greater extent. And the unit of resistance is the ohm, and which is defined as volt per ampere. So R, the resistance, is equal to volts upon current. So let's say, for instance, if we have R is equal to V upon I, we know resistance, right, is measured in ohms. And an ohm is equal to a volt per ampere, which means in this case here, if we say volts or voltage is measured in volts and current is measured in amperes, then volt per ampere gives us ohm. So resistance is measured in ohms. And from this relationship, we say R is inversely proportional to 1 upon I. Right, so this relationship says R is inversely proportional to I, right, if V or voltage is constant. Alright, so if the voltage is kept constant, then resistance in a circuit is inversely proportional to the current, which means as R increases, I decreases, or conversely, as I increases, R decreases. Right. So if we have the two are inversely proportional. Now, if we look at, let me just illustrate that. Okay, we said as I increases, R decreases, and as I decreases, R increases. Right? So if we have, for instance, a circuit here, and let's say the battery voltage is 12 volts, and let's say we have a resistor here, and let's say that particular resistance is 2 ohms. Alright? So if we want to know what is the current, I is equal to V upon R, which means it's the battery voltage is 12 volts and the resistance is equal to 2 ohms, which that means that the current is 6 amps. Now let's say we've got a circuit here, and in this circuit we again got a 12 volt battery, but this time we got a resistance of 4 ohms, right? 4 ohms. So if we need to know what's the current in here, I is equal to V upon R, which means 12 volts. Okay, 12 volts upon 4 ohms upon 4 ohms, and that gives us 3 amps. As I've illustrated here, if V is constant, then R is inversely proportional to I, which means in both these situations we have 12 volts, that means it's 12 volts and 12 volts, but in this circuit you got a resistance of 2 ohms, and in this circuit here you got a resistance of 1 ohm, 4 ohms. Okay, so you got a resistance of 4 ohms. So which shows you here now, when the resistance is low, you got a higher current, and when the resistance is higher, you got a lower current. So the relationship indicates that if V is constant, I is inversely proportional to R. We could either, in this situation, also say I is inversely proportional to 1 upon R. Same at the top, I said R is inversely proportional to I, right? So now we go to use of resistors. Okay, so resistors are both desirable and non-desirable. Right? If the resistance is in high voltage lines, what happens is that the voltage lines get very, very hot, and then there's a lot of thermal energy that's lost to the surroundings. That energy could have been useful in propagating the current, but a lot of energy gets wasted because if the lines have a high resistance. And if a geyser element has low resistance, we know that it won't heat up, right? And then resistors, they protect components, right? And they regulate the amount of current flowing through through them. But resistors also regulate the potential difference across components so that they can function efficiently. Right, let's just illustrate that. The last one. Resistors regulate potential difference across components. So let's see what we mean by that. Say, for instance, we have a battery, and let's say it's also 12 volts. Okay, and let's say we have an element in here. It could be a very small loudspeaker, it could be a bulb, it could be some instrument, and let's say it has an ohm, a resistance of 2 ohms. Now let's say, for instance, this particular element that has a resistance of 2 ohms has a rating, right? Most of these appliances have ratings, right? So it may have a rating, and the rating could say, all right, for this particular bulb or whatever the element is, it needs a voltage of 8 volts, and it may need a current of, so it needs, let's say, it needs a voltage equal to 8 volts, and it needs current equal to 4 amps. So that would be the rating for that particular element, and that would mean if you have 8 volts across that element and a current of 4 amp, then this particular element would be functioning efficiently. Right, but what happens is, in this case here, if we take I is equal to V upon R, that would mean the voltage is 12 volts, right, and the ohms resistance is 2 ohms, and that gives us 6 amps. And that's not very good, because for this to function effectively, you have to have current going through it as 4 ohms, and as we know here in this case, the voltage is going to be 12 volts, so the voltage is too high and the current is too high, so it's not going to function effectively. So let's say, for instance, we look at this again here. I have that, and here we have this 2 ohm resistor, and we got that 12 volt battery. So what happens here, for instance, and we know in here, here we need a voltage of 8 volts. We need a voltage of 8 volts across there. We need 8 volts. We need 8 volts, and we need a current of 2 amp going through this particular resistor. So what happens is, in order to have the correct current going through the circuit, and we need 4 amps, right? We'll have to have a resistor here, right? So if we have a resistor here, so say we don't know what is its ohms, right? We don't know what the ohms are. But what we know is that if we add a resistor to this, it will decrease the amount of current. We have 6 amps here at the top, and if we add a resistor, we're going to decrease that current. And wherever you have a resistor, you always have a voltage drop, right? So what we essentially want is a certain voltage dropping across this resistor, and we know that if we have a voltage drop there, the voltage drop across this resistor and across that resistor must give us 12 volts. So we have to get a resistor that has an ohmage, or the magnitude of that particular resistor must be such that the 2 ohm resistor has 8 volts across it, and the current in the circuit should be 4 amps. So that is the way a resistor can be used to regulate the current, and so that other elements can function efficiently. But we will deal with this later. I'm just giving you an indication as to how a resistor can be used to regulate voltage and current in a circuit. Right, now we know we're looking at a microscopic description of resistance. Electrons, they move through a conductor and they collide with charges and they collide with the nucleus. So what happens in this case, during the collisions, you find that they transform kinetic energy to thermal energy. So what happens is these electrons are moving and they collide with the nuclei. And as they collide with the nuclei, we find that the nuclei is also set into motion. And then we have a random motion within the material, and the kinetic energy of the electrons are then transformed into thermal energy, and then the thermal energy, the material heats up, and then the thermal energy or heat gets dissipated to the surroundings. And also the filament of a light bulb has very high resistance, and there is substantial transformation of kinetic energy to thermal energy. Right, here we just have a microscopic description where we have these electrons moving through the material, and here they colliding, and as they collide we find that the nuclei also increases its energy, and this random motion of these particles then the kinetic energy is then transformed into this random motion of these particles, and then the thermal energy gets dissipated into the surroundings. Right, let's look at this now. Here we got our bulb, and if you look at it, we got a glass bulb there, and we got our tungsten filament here. That's our tungsten filament, right? What happens is you got this wire, and the current goes through, and it goes through your filament, and as it goes through the filament, here you find that the kinetic energy of the particles are transformed into thermal energy within this tungsten, and then it becomes so hot that it starts emitting light. Right, so this happens in an incandescent bulb. And this tungsten that you have has a high melting right, it has a high melting point. And that's good, because you don't want that metal to melt at a low temperature, because if it melts at a lower temperature, it's going to break, and as it breaks, there's going to be an open circuit, and if there's an open circuit, you know that current won't flow, and therefore the bulb or globe will not light up. Let's look at the factors affecting resistance. Okay, so here we have the length of a wire, the longer the length of the wire, the greater the resistance. Okay, which means if we have a wire, say if we have a wire here like that, so it has a resistance. But if the wire is longer, it will have a greater resistance. Then we say thickness or cross-sectional area. The greater the area, the smaller the resistance. So if we have maybe a wire that say has that cross section, right, and another one has that cross section, and the width is increased, we find that this will have a lower resistance than that one. Okay, so and then if we look at the temperature, the hotter the conductor, the greater the resistance, right? Because the hotter it is, there's more thermal energy, and because there's more thermal energy, it's more difficult for the electrons to move through. And then the type of material, right? Also offer some greater resistance, right? Some material offer greater resistance. And then look at copper, silver, and are excellent conductors, right, of electricity. And I've just alluded to tungsten is also a metal, but it has a very high resistance and a high melting point. Okay, now let's look at resistors in series. When we talk about resistors in series, what we mean when resistors are connected in series, what's important to know, there is only one path for current to flow, right? The current is the same at every point in that circuit. And the voltage is divided across the resistors proportionately. Right, the voltage across the battery, right, the voltage across the battery in the circuit is equal to the sum of the voltages across the resistors. Right, you need to know that. So the voltage of a battery, which is the total voltage, it will be equal to the voltage V1 plus V2 plus V3. Those are the voltages across the resistors. So your total resistance, let's say, it's R1 plus R2 plus R3, right? Which means if you got R1 and it's got a voltage across it which is V1, and R2 has a voltage across V2, and R3 has voltage across it which is R3, right? Now let's look at this. Say for instance, now we have these circuits below, okay, and the voltage of the battery is 9 volts, okay. Each resistor has a resistance of 10 ohms, right? If we measure the potential difference across 1, 2, and 3 resistors respectively, they would be the same, right? I'll illustrate that. And so we know that the total potential difference is the same across 1, 2, or 3 resistors. Right, now let's see what we mean. If we have, let's call this point, say, A, and let's call that point B. If we have a voltage here I mean a voltmeter here, and let's call this the voltage of the battery, right? If we now have a voltmeter connected across this resistor, say a voltmeter there, and then that's connected there at point B, we will find that if this voltage here is 9 volts, we find that the voltage across this particular resistor is also equal to 9 volts. Right. And this is a 10 ohm resistor. Okay. So whether this resistor is substituted and it becomes a 10 or a 20 or a 30 ohm resistor, it will still have the same voltage of 9 volts across it, because that is a voltage that is across the a battery, right? And so the component will have that same voltage. Let's look at this one here. Again, let's call this A, and let's call it B. And let's say if we have a voltmeter here, and let's say there's also 9 volts, and it's 9 volts, and let's say so here VB, let's say VB is equal to 9 volts. Now if we now take the voltage across this, if we take a voltage across these resistors here and we connect it to the same point, this voltage will also read 9 volts, right? Because there's the voltage across the battery. So both these resistors will have a voltage of 9 volts. Let's say this is R1, and let's call that R2, right? Resistance 1 and resistance 2. And let's say, for instance, if we connect a voltmeter here, and let's call it V1, right? And let's have a voltmeter here and call it V2, right? Which means that if we have V2 here, it would mean voltage across resistor 2, and V1 is voltage across resistor 1. So if we want to look at the relationship and we say, okay, in this case, if we want to know what is R total is equal to R1 plus R2, right? Which means that we know that each resistance is 10 ohms, so 10 ohms plus 10 ohms for R2, which tells us the total resistance of this particular circuit is 20 ohms. And if we look at the voltage of the battery is the same as the voltage across resistor 1, right, plus the voltage across resistor 2, right? And we know that the voltage across resistor across a battery is 9 volts. And we also know that the voltage across the two resistors is also 9 volts, right? But since R1 is equal to R2, right? The resistance are the same. We can say that the voltage for each one would be 4.5 volts plus 4.5 volts, which give us a 9 volts. If these voltages were not the same, then the battery voltage will have to be divided proportionately. Okay. Let's look at the next one. So let's say here again we got a voltmeter, okay, and we got a 9 volt battery again, and that's again the voltage of the battery. If we now connect here, and let's say we move, and I got a voltmeter across all these, right? And see, I'm connecting it to the same point, so we know that here it's also going to be 9 volts. And let's say this is R1, and let's call it R2, and let's call it R3. If I have a voltmeter here that's connected to resistor 1, let's call it V1. And let's say I have a voltmeter there, and let's call that V2. And let's say if I have a voltmeter across R3, and let's call it V3. Right, but what we do know is that, let's also just call those points A, B, right? We could call them A, B, we don't have to, right? But A, B, so what do we know? That the voltage across the battery is equal to the voltage across all three components, right? So the 9 volts is it's the voltage, across all three resistors, right? And it's 9 volts. So we say, okay, R total is equal to R1 plus R2 plus R3, which would mean we know each resistor has got resistance of 10 ohms plus 10 ohms plus 10 ohms, which is then equal to 30 ohms. That's the total resistance in the circuit. Now if we want what's the voltage of the battery we know, and the voltage of the battery is equal to the voltage across resistance 1 and across resistance 2 and resistance 3. What we know that the voltage of the battery is 9 volts, right? So we also know that the voltage across the 3 is 9 volts, right? So, but since R1 is equal to R2 is equal to R3, that means each one is going to have 3 volts plus 3 volts plus 3 volts, which means a total of 9 volts. Right. Now if we look at here, we've got 3 resistors. So let's say this one is 5 ohms. Let's say that is 7,5 ohms, and let's say this one is 10 ohms. Now it says what is the total resistance in a circuit. And at this stage you can see we haven't been given the voltage, but we're not worried about that because we just need to calculate the total resistance. And for this, if we, let's say, call this R1, call that R2, and let's call it R3, then R total is the resistance in a circuit, which means R1 plus R2 plus R3, which means we got 0,5 ohms plus 7,5 ohms plus 10 ohms, which gives us 18 ohms. So the resistance in the circuit is 18 ohms, right? For this, and it's a series circuit, and we know if it's a series circuit, if I have to put an emitter anywhere, whether there or there or there, it will have to measure the same current, right? Okay, now let's look at this one. Here the resistance has a resistance of 75 ohms, okay, and the other one has a resistance of 1,7 ohms. Okay, and if we need to know what's R total would be, let's say we call this R1 and we call that R2, so it's going to be R1 plus R2 is equal to 75 ohms plus 1.7 ohms, which gives us 76.7 ohms. Right, now here in this case, I mean, we don't know what the voltage is here across this resistor, and we don't know what the voltage is here across that resistor, right? So we know that the current in this particular circuit, and if we're using conventional current, goes in that direction. We know that this is the same current everywhere because it's a series circuit, and we know that the voltage across the 75 ohms would be greater than the voltage across the 1.7 ohms, and together they will add up to give us the cell voltage, but we're going to get there. We'll elaborate further when we get to those questions. Now let's look at the next one. Here in this case we have, let's say, this one here is 75 mega ohms, right? Mega is 10 to the 6 ohms, so 75 times 10 to the 6 ohms, and we have 1.7 mega ohms. If you want to know what's R total again, let's call it R1, and let's call that R2, right? Let's call this R2. So R total is equal to R1 plus R2, which is 75 mega ohms, 75 mega ohms plus 1.7 mega ohms, which gives us 76.7 mega ohms, right? Which is actually 76, which is actually 76.7 times 10 to the 6 ohms, which is the same as 7.67 times 10 to the 7 ohms, if we're giving it in terms of ohms. Right, now let's look at, I'll be showing you some PHET demonstrations, but here we're looking at showing you resistors in series, and resistors in series are actually potential dividers, right? That means we know that in a series circuit the current remains the same, but the voltages divide. Right, so let's see. So what I'm saying here, so let's say in this case we got the voltage of the battery is 9 volts, and I'm showing you the direction of the current is conventional current, and here we've got one resistor that has a 10 ohm resistor, and the voltage across the 10 ohm resistor is 9 volts, which is equal to our battery voltage, and the current here is reading 0.9 amps. Right. So what we're saying is our voltage of the battery is equal to 9 volts. Okay. And if we want to now know what is the current in the circuit, we say I is equal to V upon R, and voltage of the battery is 9 volts, and the resistance in the circuit is equal to 10 ohms, which means the current in the circuit is 9 amps. Okay, so there we have 0.9 amps. Now let's look at the next one. Here we've got the same voltage, but here we've got two resistors in series, right? And the voltage across both those resistors is 9 volts, like I illustrated earlier. And then the current in this particular circuit is 0.45 amps, right? So if we look at this here now, we say R total is equal to R1 plus R2. Okay, I could have taken anyone, that is R1 and that is R2, which means in this case we got 10 ohms plus 10 ohms, which gives us 20 ohms. Okay, and so that is the resistance in this circuit. If we want to now know what is the current, we know that VB is equal to 9 volts. Okay, which means I is equal to V upon R total, which would mean that we have 9 volts upon 20 ohms, which means we have 4.5 amps in the circuit, right? 4,5 amps in the circuit, which means here, as you can see, it's reading 4,5 amps. Had I moved this prod to there, it will read 0.45 amps, and there it will read 0.45 amps, or there it will read 0.45 amps. Now, as you can see, the voltage across both these resistors is 9 volts, right? But if these two resistors are equal, right? So let's say R1 and R2 is equal, we find that here I show you that the resistance is 4,5 volts, right? It's 9 volts across both, but because these are equal, so if I take this voltmeter and I put it there as well, it's going to read 4,5 volts. Because in total, that would be equal to 9 volts. Right, here we have again 3 resistors, 10 ohms, 10 ohms, 10 ohms, right? And we see the current is 3 ohms. As you can see here, the resistance there was 20 ohms, current is 0.45. Here the resistance is greater, but our battery voltage is the same. So our total here is equal to, let's say we call this R1, R2, and we call it R3. Then we have R1 plus R2 plus R3. Each resistor we know has got a 10 ohm resistance plus 10 ohm resistance plus 10 ohm resistance, which means the total resistance is 30 ohms. And then voltage across the battery is then equal to voltage across 1 plus voltage across 2, resistance 2, and voltage across resistance 3. And we know this is 9 volts. And as you can see, we have 9 volts across all 3, and all are equal. So that would mean this would be 3 volts, plus that would be 3 volts, and plus that would be 3 volts. So here you can see that if we have resistors in a series circuit, they are potential dividers, right? Each one has its own potential drop. That's a certain voltage gets dropped at that particular at a resistor. So here I have shown you. So there I show you it's 3 volts, and there it would also be 3 volts, and there it would also be 3 volts. Right. So what happens is the voltage of the battery gets proportionately dropped at the respective resistances. Right. So now let's look at a demonstration. Okay. So here now we have demonstrate what we did there. So let's say I've got a battery, right, and I've got copper wire there, and I've got copper wire, right, and let's say we have this, right, and there we have copper wire here, and we have this, and right, and now let's say I have a resistor. I put a resistor in the circuit, and then I put a wire there. Okay, and I have this wire there, and let's complete the circuit. Right, there you see the electron current flowing, right? But we are going to be dealing with conventional current, so let me change that to conventional current. Right, it means the charges are moving from the positive terminal of the battery to the negative terminal. Now here you have the current moving in this particular circuit. Right, but now we need to have a look, and we see what is the voltage of our battery, and we see the voltage of the battery is 9 volts. Right, so the voltage of the battery is 9 volts, but let's see what's the voltage across the resistor, which is our component. And as I have alluded to earlier, we expect it to be 9 volts. Right, there's 9 volts. What you need to also realize is that wherever there's a resistor, a potential, there will be a voltage dropped at that particular component, right, or that resistor. See, if I take and I connect it here and I connect it there, there's no resistance. As you can see, the voltmeter registers 0. So in a conducting wire, the voltages, there's no voltage across any position of the conductor, right? So the voltage is 0 there. There's only a voltage drop where we have our resistor, right? And if we now take this current and I use this emitter and I want to measure the circuit current, see what it's showing. It's showing 0.9 amps. Whether I take it here or take it there, it's still showing 0.9 amps. Whether I take it there or there, it's still showing 0.9 amps, right? That means anywhere in the series circuit, the current remains the same. Let me do this in symbolic form, and let's say I have it there. You see I've the battery, and then we've got our resistor, which then shows us that the current in the circuit, anywhere in the circuit, is 9 amps, right? And let's say, for instance, let's put the values in. I'll put the values in so we know what the values are, and there we go. The voltage of the battery is 9 volts. The resistance of the resistor is 10 ohms, right? So here you have a current of 9 amps. Now let's say, for instance, I want to leave the voltage as is, right? But I want to increase the resistance. So we know if we increase the resistance and the voltage is the same, what happens to our current? Our current decreases. So let's say I increase the resistance. I'm going to increase it. You can see it's 10 ohms, so I'm going to increase it. And if I increase it, what is happening to my current? My current is decreasing, as you can see, right? So as the resistance in a circuit increases, the current decreases, right? I told you that there's an inverse relationship between resistance and current, right? So and there we have that. So let's say, for instance, if I keep the resistance the same and I increase the voltage, right, and the voltage is 9 volts. So let's see what happens if we increase the voltage. If I increase the voltage and look at what happens to the current. If I do that, as you can see, by increasing the voltage, the current in the circuit increases, and the charges are moving faster, right? Okay, so there we have it. Right, now what I'm going to do is put two resistors in series in this particular circuit. Okay, so I'm putting that back and that, and now let's put another resistor here. So let's say we have put another resistor, cut that piece. I'm putting another resistor. Okay. And there I put another resistor, right? Two resistors. Now let's get back again and see if my voltage across my battery is still 9 volts as it shows there, but now my voltage across two resistors should be the same as my battery voltage, so it's 9 volts. And what's my current? My current, now I've got two resistors. As you can see, my current has dropped. So whether I have it here, or whether I have it there, or whether I have it here, it will be the same current, because it's a series circuit. Right, so the current remains the same in the series circuit. But now we know that the voltage across both those resistors is 9 volts, but both those resistors, the one is equal to the other. So what would the voltage be only across one of these resistors? Right, so let's check it, and there we go, it's 4.5 volts. So it's 4.5 volts here, and it's 4.5 volts there, so which means it is 9 volts in total. Right, and the same thing applies. If I increase the cell voltage here, and if I increase, see what happens to the current increases. Right, and the current increases, and if the resistance is kept constant, right? So there we have that, and we've got our voltage to be 9 volts across both the resistors, right? And like we said, if we have resistors in series, they are potential dividers. That means the 9 volt of the battery is now distributed over two resistors, and it's 4.5, 4.5, whereas the current in this particular circuit remains the same. Right, and let's go to the next one. Let's have now 3 resistors in series. So if we have got 3 resistors in series, so let's say, there we go. Right? And here we got now 3 resistors in series. And there you can see the current is moving much slower, right? We got now 3 resistors in series. So let's see again, if we look at the voltage here across our battery, it shows 9 volts. But we know if we want to find the voltage across our 3 resistors, there and there, we know it has to be 9 volts. Right. And because they all equal resistors, we know that each one is going to have 3 volts. So that's 3 volts. That's 3 volts. And that's 3 volts. Right, so in total, they 9 volts. If we're looking at the current now, we know that the resistance has increased, so we know that our current is going to be less. There, 0.3 amps, whether I put it there, still 0.3 amps. If I put it in between our resistors, it's still 0.3 amps because there's the current in the circuit. Right. So current in a series circuit is the same throughout. The voltages of the battery gets divided and the sum total of the voltages at each resistor equals to the battery voltage. Right, and now let's say, for instance, I just want to increase the voltage, right? And if I increase the voltage, let's see what happens to the current. As you can see, the current increases, right? And see, I have the voltage there, so there's 31.5 volts. Okay? And if we look at, if I now decrease the voltage back to that, we got our current. Right, now let's say, for instance, if I decide to increase a resistor, let's say it's a 10 ohm resistor, right? Now I'm going to increase the resistance. So I'm only increasing one resistance, as you can see. I'm increasing one resistance. If I increase one resistance, see what is its ohms, right? So each was 10, and this has now increased to 14.5. So the total resistance in the circuit has increased, and as you can see, the current has decreased, and it is now 0.26 amps. But at the same time, now let's say, for instance, see what's the voltage across the 14.5 ohms, right? So whatever the voltage is across the 14,5 ohms plus the 210 ohms, they must add up to the battery voltage. So let's say, how much is it? 2.61, right? Across that is 2.61. Right, so it's 2.61 plus 2.61. And here we have 3.78. So 2.61 plus 2.61 plus 3.78 is going to give us 9 volts across the 3 resistors. And there you have it. See you next time.